let's get on with the lecture. We had just got done talking about the derivatives of exponentials, right? Because we had talked about this equation or this problem.
Yeah, it's a good example.
And then talked about the normal probability density function, right? Where the bell curve comes from. Which is just as disgusting looking of an equation as what everybody would expect, right? Cool. So, section 4.4. Start off with, I want to ask a question. We know b and we know y. Are we going to undo the exponential to find x here? Square rooted? Not quite. So, write all of this out. You're on the right track though. Like it is going to be something akin to. So let's write this slightly different. Let's imagine we've got x is equal to b raised to some y. What we want is a function that will spit out y. How might we do that? Any thoughts? So set square root, something like that, but it's not a root. What's called a logarithm? Logarithm, the way this reads is log base b of x is equal to y, is equal to y if and only if x is equal to base b raised to the yth power. So all this thing is answering, it's given a base b, and that it's raised to some power, we don't know what it is, but we do know what it comes out to be. Given that we know what it is raised to that power, we know what the base is, what's the power? So it's kind of akin to a root, but not quite. What it's doing what it's doing is undoing the exponential. It is the inverse function of the exponential. Make sense? So since this thing is the inverse function, well, before I get to talking about the graph and everything else, just some details on the notation of this. In the case that we're using base 10, because it's a common base, we'll just drop off the base notation and write log of x instead of log base 10 of x. If the base is equal to e, we write the natural log of x, which is log base e of x. And because mathematicians are lazy, instead of calling this natural log all the time, we oftentimes will just call it ln.
Why wouldn't it be NL? For natural log, it's log natural.
I think just because all the other logs, like we just started off with log and we're like, it's a log natural base. So having said that, the natural log of x is equal to b if and only if e raised to the b is equal to x. Same idea as this, right? Except here we're using e. Having said that, just some observations worth noting on. The ln of 1 is going to be equal to 0 because e raised to the 0 is equal to 1. The ln of e is going to be 1 because e raised to the 1 is going to be e. 1 over e is negative 1. E to the negative 1 is 1 over e, so forth and so on. Now, an observation to make. Well, again, I'll point this out for just a second when we get to next slide. An observation worth making here is that if our base is greater than 1, then b to the x is going to be between 0 and 1 whenever x is less than 0, right? Agreed? So because of this, the domain of e to the x is going to be negative infinity to infinity, and its range is going to be 0 to infinity. Having said that, the logarithm is the inverse of the exponential. So its domain and range is going to be the reverse of the domain and range of the exponential. The domain of the exponential will be the range of the logarithm, and the range of the exponential will be the domain of the logarithm. Another fun fact here, anytime you have a function and its inverse function, if you know the graph of the function, the graph of its inverse function will be reflected across the line x equal to y. So because we know the graph of the exponential, we know the graph of the logarithm. Cool. Having said that, awesome, sweet, yes, next slide has this. All right. So, let's look at A really quick. We're given that some function of x is equal to the ln of x plus 1. This is going to spit out all of our y values, right? So let's solve for x and find the inverse function of this. Solving for x, we're going to get that I'm raising both of these to an exponential will look like this, right? This is the inverse of that, right? The exponential is the inverse of the logarithm, the natural log. So all that's going to remain is going to be x plus 1 is equal to e to the y. X is equal to e to the y minus 1 then, right? So our inverse function is going to be this, but we're going to flip our x and our y's, right? We're going to swap them out. Now this thing, we know how to graph. We know that e to the x is this graph, right? So if we subtract it by 1, we're just lowering it by 1 unit. Agreed? Now, we want the graph of this, which is going to be the reflection of blue across the line x equal to y. So let's put x equal to y here. So the graph that we want is this graph here in yellow. Make sense? So this is one method for finding it. The other method is to use a tabular approach, like what we have here, where we just find a bunch of x values, plug them in, and check out what our logarithm evaluates out to be. Having said that, since we know what the logarithm generally looks like, we have an idea of what this is going to come out to look like, right? Once we plot these. But just really quickly comparing what I've got in yellow compared to the graph here, exact same pretty much, right? Barring a few details. Namely, those details are that we have an asymptote here and another asymptote here. And the only reason we have this asymptote is because e to the x is asymptotic to our x-axis as we go to negative infinity. Well, we just move that down by 1 unit. We subtract 1. And then it gets reflected as well. And my lines aren't perfect here, but it gives you the general idea. So having said that, again, some quick properties. These things are inverse functions of each other, right? The logarithm and the exponential, they are inverses. So because of that, anytime you take the ln of e raised to anything, you're going to get that anything back. Anytime you take e to the ln of anything, you're going to get that anything back. So because of this, problems like this become pretty quick, right? This is just going to be the square root of 2. This is just going to be 3x, right? Square root of 2, 3x. Having said that, some properties of logarithm. Now notice this property is a result of these two. To see that, let's rewrite the ln of x over y. We can rewrite as the ln of x times y to the negative first power, right? Applying that first property then, this is going to come out to be the ln of x plus the ln of y to the negative first power applying the third property, we get that this is the ln of x plus negative 1 times the ln of y, which is just the ln of x minus the ln of y. So really, we only need to memorize property 1 and property 3. Because property 2 is a result of these. Yep. Having said that, I'd like for y'all to work on A and B really quick. I'm going to do C and D up here on the board. So for A, who got the ln of 10 minus 9? The ln of 9. For B, 1/2 the ln of the quantity x squared plus 1. Anybody get that?
Wouldn't that just be the square root of x squared plus 1?
Not quite. So the ln only undoes e raised to a thing, right? And using these properties, all we're going to get back is 1/2 of ln x squared plus 1. Does that make sense? Kind of answer your question a little bit? Kind of, sort of. Comparing really quickly then what they did for C and D to what I did, same thing, right? Notice whenever we have an addition or a subtraction happening inside the ln, we can't break that up. We have to leave the ln of the quantity x plus 1 together, or x squared plus 1 together, so forth and so on. Having said that, there is an exception. Kind of, sort of. What if I had said, what's this? Almost there. So what we've got to do is the first thing we have to see is that this thing, x squared minus 2x plus 1 is equal to x minus 1 squared. And then we can do the rest of this. We can get 2 ln x minus 1. So there are some tricks in here as well, right? Like if the thing inside is something raised to a power, go ahead and pull out that power when you can, like in a case like this. Having said that, generally, we're going to see stuff like this, and we can't do anything to that. So as another example of something we can't do anything to, well, that's not entirely true. Can do something to this, can't we? X squared minus 1 is equal to the quantity x plus 1 times x minus 1, right? So we can rewrite this then as the ln of x plus 1 times x minus 1 so this is going to come out to be the ln of x plus 1 plus the ln of x minus 1. So these are the only times we can actually do stuff with addition or subtraction inside the ln. It's only when they factor out in particular ways, like those last two examples. Yep. Having said that, these properties move forwards and backwards. So looking at B really quick, some of the philosophy we should lead into the hard things. We've got B is 2 ln x plus 2 minus 3 ln x this is going to come out to be the ln of x plus 2, that quantity squared, minus the ln of x to the third all this is going to come out to be the ln of the quantity x plus 2 squared divided by x cubed. Yeah? Comparing, same thing. Nothing revelatory here. All right, so what if we want to use this stuff to solve for variables? Let's look at this case B here really quick. We're told that 10 plus e raised to the t over 10 is equal to 14. I just went ahead and turned that decimal into a fraction, right? This tells us then that e t over 10 equal to 4. I subtracted 10 from both sides. Now, we want to apply the ln to both sides. Why do we want to apply the ln to both sides? Folks at home, what do you think? Why do we want to apply the ln to both sides? It's because the ln is going to undo the exponential. So what we're going to be left with here is just t over 10. So, multiplying both sides now by 10, we get that t is equal to 10 times the ln of 4. And that's it. So comparing really quick. They left everything in a decimal form. I would highly suggest not doing that. And the reason why I would suggest not doing that is because we could change the decimal very easily to something like ones repeating. So for those who don't know, anytime you have a bar over a grouping of decimals like this, it means that grouping just repeats on and on and on forever. Anybody know what that is as a fraction?
Not 9/10.
1/9.
1/9. You were right about the 9. It is 1/9. One way we can see that is we can compare it to something we know. So for example, .3 repeating. We know this decimal is a third, right? And we know that this decimal divided by 3, it's going to come out to be 0.1 repeating, right? So what we get here is this is 1/3 times 1/3 or 1/9. So the reason why I would suggest turning all of these decimals when you can into fractions is because imagine you got to this point and it was 0.1 repeating. If you didn't know right away to use 1/9, this would take a little while to figure out, right? So when possible, go ahead and jump to fractions. What time is it? 13 more minutes. Okay, we can get through these. So let's look at B again. In this example, we've got 3 plus 2 ln of x is equal to 7. First thing we want to do is subtract 3 from both sides. Now let's stop here for a second. This has 2 different routes we could take, doesn't it? We could either rewrite this as the ln of x squared is equal to 4, or we could divide 2 from both sides. Now, raising e to both sides, and we get e to the ln of x squared is equal to e raised to the 4th, right? Same thing down here. E raised to the ln of x is equal to e squared. And the only reason we did this is because taking e to the ln of something will get rid of that ln, right? So all you're left with is that something. So on both sides here, we're going to end up with x squared is equal to e to the 4th, or x is equal to e squared. Notice by dividing that 2 out right away, it's a little bit quicker, right? Because we still have some massaging to do here. We still have to take the square root of both sides. But because we're taking the square root of both sides, we're going to get plus or minus. And now we have to decide which answer to keep, or if we keep both answers, or throw both answers out. Well, x here can't be negative, right? Because the ln of a negative thing doesn't exist. Negative numbers aren't in the domain of the ln. So that means all that gets left over here is going to be x is equal to e squared. Took a lot more work. Moral of the story here, when you get to cases like this, divide out instead of using the property rule to pass it through as a power. The power property is what I should have called it. Property rule. Does this make sense? Kind of, sort of? All right, really quickly comparing. Notice that's exactly what they did here, right? They went ahead and divided both sides by 2. And went all the way through. Work smarter, not harder. That's the moral of the story. All right, so common question. When the hell am I going to need this? What is this good for? Well, the common question we might have is trying to figure out how long it will take an account incurring interest to double. So we know that the amount in an account that's compounding interest continuously is the original deposit times e raised to the RT. Agreed? Well, we want to know how long it's going to take for the amount to be equal to 2 times what we put in, right? So that tells us A has to be equal to 2p. What we want to solve for is t. Yeah? All right. Cancel out both p's. Now we want to get rid of that exponential. So to undo it, we're going to apply the ln to both sides. Divide both sides by r. And that's all it is. Because we're not told what r is, we're not told what p is, we're not told any of that. We're just looking for a general equation that will tell us how long it's going to take to double the amount. So no matter what the interest rate is, the time it takes to double what you put in, it's just going to be the ln of 2 over r. Now let's take a second to think about this. Why would that be? Well, let's set t equal to the ln of 2 over r. Then a is equal to p times E raised to the R, ln of 2 over R. Okay, our R's are going to cancel. So this is going to come out to be P times E raised to the ln of 2. Well, E to the ln of anything is just that anything. So just as a way of verifying it, right? Comparing our answer to theirs, we came out with the same thing, right? Then they went ahead and just looked at a bunch of different interest rates. At 3%, it would take you 23.1 years to double. At 12%, it would take you 5.8 years to double. Most of your student loans are around 7% to 3.5, 3.5 to 7. So if you don't pay anything off in 10 years, you just doubled your student loans. Moral of the story, do not put them in deferment for 10 years. It'll double. What you have right now will double. Don't do that, that's bad.
As long as you stay in school, even for one semester, you don't have to keep paying them. You
Right.
just keep waiting.
Right, that is one of the nice things. They
It
don't
doesn't
incur
incur
interest.
interest rate either.
To a point. There's a bunch of rules about that that are really weird. If you're out of school for a certain amount of time and then go back, they can incur interest under certain circumstances. It's weird.
I'm saying as long as you're staying in.
Yeah.
Like, every semester, just that one weird class.
But like I said, moral of the story, as an example of where you're going to use this applies to all of you. Student loan debt. Having said that, we do not have enough time to get through any more materials, so I will let y'all go. I'll stick around if y'all have any questions.